Okay, now let's talk about Avogadro's law. This is the last laws of the four gas laws that we studied this semester. So let's take a look at how to think about Avogadro's law. Take a look at this representation here. Okay, notice what has changed in state 1 versus state 2. We've been doing these states 1 and state 2, so I won't go into much detail, but now just to ask you, what do you notice has changed from state 1 to state 2? So hopefully you've noticed that in state 1, 6 uh, molecules of gas there, and it seems to be more than 6 molecules of gas here, right? So it has increased. In fact, it has doubled the amount of gas molecules. So if we were to measure it, maybe we can measure it and it reads 1 mole, it has doubled to 2 moles. So the amount of moles or the amount of gas has increased. What then is the same? Well, if we keep the pressure the same and the temperature the same, how will the volume change? Let's think about that. You have more gas molecules, it will bounce against the wall much more frequently, correct? And if it bounces more frequently, then the pressure will increase. But we want to keep the pressure the same in this case because Avogadro's law says that pressure must stay the same. So in order to keep the pressure the same, you would have to increase the volume, right? When you increase the volume, the gas molecules have to travel a little bit more farther in order to hit the wall. So therefore, its frequency of hitting the wall is now decreased. Even though there's more of it hitting the wall, eventually it will come into equilibrium so that the pressure will stay the same. So from this picture, we see here that volume has indeed doubled. So when moles doubles, the volume also doubles. This again is a direct relationship. Again, mathematically, we can do the same consideration we've done before. We take n divided by v, you get a number, n2 divided by v2, you get the same number, so we say they are constant. Because they are constant, we can write an equation, and this equation is n1 over v1 is equal to n2 over v2. This, in essence, is Avogadro's law. And as always, we can always say the flipped, where volume is on top and moles is on the bottom. So let's do an example of Avogadro's law. A weather balloon with a volume of 44 liters contains 2.0 mole of helium. What is the final volume of the balloon if 3.0 mole of helium is added, if pressure and temperature is constant? Notice that since I said pressure and temperature is constant, you can then use Avogadro's law. Let's again go to the board to solve this problem. Okay, so Avogadro's law here, again, writing down all the facts that we are given. A weather balloon with a volume of 44 liters. That's the volume of V1. That's our first volume of 44 liters. And contains 2 moles of helium, so that's our N sub 1. What is the final volume? There we go. We don't know V2. If the balloon is added with 3 mole of helium. So you add 3 more moles of helium. So many students would make the mistake in saying that N2 is equal to 3 moles. But hopefully not you, right? Because that's added. What was there before? It was already 2 in there before. So really, N2 is 5.0 moles. Okay, don't be tricked by that. We're solving for V2, so I would like to choose the equation where volume is on top. Volume on top is V2 over N2 is equal to V1 over N1. Again, to isolate V2, you multiply both sides by N2, because N2 and N2 will cancel each other out, giving us this relationship. So then we just have to plug it in. What is V1? V1 is 44 liters times N2 is 5 moles divided by N1 is 2 moles. Okay, we do that and we get, again, moles and moles cancel out. Liters is our unit, so we get 110 liters. Sig figs, 2 sig figs here, 2 sig figs there. Alright, good job. Let's do a checkpoint. Avogadro's law states that the volume of a gas is directly related to the moles of the gas present. If the moles of the gas present is cut in half, what happens to its volume if pressure and temperature are constant? Okay, so take a moment to think about that. Remember that volume and moles are directly related, so if you decrease the amount of gas by half, then the volume should also decrease by half. The answer is D. The volume is halved. Very good.